Okay, let's talk about the load modeling. So we spent many lectures on the generation modeling because generators are very complex, which are the key players of the power system, especially for stability study. Loads are not considered as important as generator, but we do need to introduce some models for load, such as we can have more accurate stability analysis. So I will cover most of the material from chapter 7 from Quinter's book, and also provide a list of references. And I will utilize some figures or some information material from those references. There are a number of IEEE transaction papers, which are actually the technical report from some task forces on the load modeling and the load performance. And also I gave a few technical reports from EPRI. I believe you can find those reports because those are pretty old reports. You should be able to download those reports if you want. Some background information about load modeling. Although loads are have not received as much attention as other power system components, such as signal generators, even transformer, transmission lines, and some other controllers. But if they're not accurately represented in the power system model, that they will affect the accuracy of the stability analysis. But it's challenging to have very accurate load modeling because there are a number of reasons. First, a power system can have a large number of very diverse load components. You can consider each load component as individual device or even a control system. So if you model every dynamic, every characteristic of that system, it can be very challenging. But for stability study, we focus on the power system, mainly at the high voltage levels of the system, including generator, backbone transmission system. But load are connected not at high voltages, so they are connected at the distributed voltage level. So we cannot have the accurate details of all the load components. So we have to aggregate all the loads to the high voltage level for stability study. For instance, there's no load which can connect it directly to 500 kV. But when you simulate a large transmission system and the backbone system is operated at 500 kV, and you want it's reasonable to ignore some low voltage details, and which means you have to aggregate the load as reduced model seen from the high voltage systems. Another challenge is the ownership or location of any load device may not be directly accessible to the electric utility company who is going to do the study. For instance, if you want to do a transmission system stability study, that is usually done by power system engineer at an independent system operator. But those system operators, they mainly manage the transmission grid, but the load are connected to the distribution systems. So they may not have that accurate information on that load. They only have maybe the current and voltage waveform measured at the substation where the load is connected, but they don't have more details. So precise information on the load composition may be unavailable, especially such a composition may change over time. For instance, even for the same substation, and the winter load and summer load can be very different. For instance, in some northern regions in the winter, so a lot of loads will be heater loads. The heater loads will behave like resistance of the circuit. But in summer, some area will have more air conditioner load. Air conditioners will pretty much based on the induction motors. So they can behave very differently. And even at different during different time, like in the morning or in the evening. So compared to the daytime or the depend on the temperature. So the load composition can be very different. The characteristic of load, there are some uncertainties. And so the data we have to model the loads usually are collected from normal condition, right? But why do you need to do a stability study? Because you want to cover abnormal condition, but you don't have enough abnormal condition. You can only somehow predict what abnormal condition can be. But the load model is pretty much based on like normal condition data. So there are those challenges, which means we don't really have to model the load very accurately. And actually, it's not practical to do that. Then we have to define a concept, which is a bus load. So here, there's which represent a portion of the system which is under one transmission substation. Okay. So when we step down the voltage from a high voltage transmission, so through a substation, and you will utilize some transformer and to decrease the voltage to sub-transmission level, usually lower than 100 kV. At the sub-transmission level, if there's a large industry customers which will connect to the grid at high voltage, so there could be a load going to the industrial customer. And then it can go to the distribution system through a distribution substation. Under the distribution substation, there can be many feeders. So each feeder will send a load to individual regions of a load customers. This entire portion is part of the power system. So if you model the entire power system accurately, you cannot ignore any element in this portion. But actually, when we study the bar power system, usually we only focus on the modeling on the transmission system, maybe and the part of sub-transmission system at high voltage level. So which means we can somehow aggregate everything in this portion by a single element, which is called bus A. The bus A basically just a simplification of that substation and everything under the substation. So, and we use some function to model how the power change from the transmission to that area. That power is considered bus load, including both active power and reactive power. So bus load is a concept which is utilized to treat the entire portion under sub-transmission, under a substation, including the sub-transmission systems and distribution system and all the customers as a single power consuming device. It's a fictitious device, which is like if you replace this entire region by a single device. So that single device can be utilized to represent what happens in that area in the stability study. So that's the purpose of the definition of the bus load. So if you want to make the bus load be accurate, we have to consider any potential elements which can be connected under this substation. So based on this figure, we know there could be a list of items you may want to consider, such as the substation step-down transformer, sub-transmission feeders, primary and secondary distribution feeders, distribution transformers, and also capacitor and regulators for voltage control. And also sometimes you also need to consider the varying connection, which means anything under this substation can be another grade, a low voltage power grade. You don't have to keep the topology and the element everyone in this list, but you definitely need to consider any one from this list may change the characteristic of your load. Okay. For instance, if you model this bus load to serve the purpose of voltage stability study, any element that can control the voltage and change the voltage characteristic need to be modeled more accurately. Okay, so when we talk about the voltage control and voltage stability, and we'll use one example to show you either just aggregate everything in this area by a very simple element, compare to the original topology of system by considering transformers and controller, the result can be very different. Okay, sometimes you may want to keep the transformer and voltage controller in the model. You don't want to reduce those by simply a load device. So there are two types of load models. The first types the static load model. Static load model, which means you don't need to consider any dynamic of the load. The load basically just give you a complex number with real part to be the IT power, ready part to be the imaginary part to be the ready power. And the P and Q are both function of a voltage right now for the current instant. If the load is also depend on frequency, you can also add the frequency as a variable. But pretty much the P and Q will be functions of V and F. Okay, it doesn't depend on time. And it doesn't rely on any history in the past for the past instance. Some loads are typically considered a static load model, such as the resistive load, like heaters or lighting load, especially like incandescent light, like a conventional light. But some new type of lighting load may not be considered maybe accurately as a static load, or there maybe if there's a better control circuit in the load. But for the simplified model to accelerate your stability study, you usually can treat such load as static load models. Compared to static load model, the dynamic load models model P and Q as function of the values of voltage and the frequency at both the current and past time instant, which means it does depend on the history, and which means only knowing the current value of voltage and frequency right now doesn't fully tell you what the load is. Okay, so it may integrate some differential equation. By solving the differential equation, you can have the trajectory of the load, and then you'll find the current time instant that will tell you the more accurate information. So in such case, such dynamic load model can be similar to generators. Like generator is not a static device, a dynamic device. So that's why usually the representative dynamic loads are motor loads, where air conditioner or with some industry. Also, there are some other dynamic loads, such as they have a controller. The controller will try to maintain the load level or maintain certain index by using control circuits. They are also considered dynamic load. There are two approaches to model the loads. The very straightforward method will be component-based approach, or we call it a bottom-up approach. Basically means we check everything in the region where we need to aggregate to become the bus load, right? So you just count how many type of elements you have. And for each type of element, and you can write down a number of functions to help categorize that element. Like for instance, there could be some motors, and there could be a different type of users, and you just use different type of functions to categorize them, and then you gradually aggregate. Finally, eventually, you only have just one set of functions modeling that bus load. So this is called the bottom-up approach. For instance, you can do the modeling after a number of stages. The first stage is you try to identify some functions which help you to model the load. Like for any load, we definitely need to know the power factor. Okay, so that's a very important index to categorize the load. And also we can consider the static load model for P, and also static load model for Q. And if there are also dynamic parts such as motors, we can maybe put the motor there, or the parameters of motor will be the parameter of the load. So next, In the next level, we focus on some load components. Load components such as a space heater. A space heater, we can utilize the building blocks we already created at the bottom level, like basic power factor and P function, Q function. And if it has a motor, we also need to consider that one. But definitely for space heater, it doesn't need a motor as a component. And it pretty much like a heater load, a resistive load. But for air conditioner, it need a power factor P and Q, or you just take the structure of the motor load, because air conditioner will be pretty much based on the induction motors. And there could be some other different type. So basically each component will be modeled using the characteristic we define at the bottom level. Then we go up to the next level, which is the load class mix. Load class mix basically talk about different category of load, like industry load, commercial load, residential load, agricultural load. So each load will have different mix of load component. For example, for commercial load, the air conditioner maybe take a majority part, right? But for the residential load, you may need like a water heater or dryer, like a washer, dryer, such type of load. Okay. So for each class, you can define the percentage of a different load component. Like for instance, if I'm talking about a commercial load, and air conditioner may take I'm just roughly put number like 60% to be air conditioner. Lighting could be a 30%, and there could be like refrigerator could be 10%. I'm just use this one example. But when you move to a different class, like industry load or agricultural load, those percentage number will change, but those components will be same. We can use the same set of components. Finally, we can go to the bus load. The bus load will be the combination of different percentage of different classes. And eventually we can aggregate the bus load into one structure. This one can be utilized in the software for simulation. For instance, this is the compliance load model provided by PTI PSSE. In this load model, it suggests we need to consider such elements like large motors, basically from industry, and also small motor for the residential users. So they together will form the dynamic load, and the remaining part will be pretty much the static load, because they don't depend on time. The load will mainly depend on voltage or frequency. So this is a bottom-up approach. This is a very classical approach adopted by the industry, the power system engineers. So if you have a new region, you want to create a model, usually this is a necessary practice they have to do to understand this region better to build up the load model. But once they finish this at the site, don't have to do it every year or often. You can just utilize the load structure, the load model structure you create at the end. And every year, maybe you just need to do some update on the parameters. So that will bring this second approach, which is a measurement-based approach. The measurement-based approach is if you already select a load structure, okay, and which involve a number of parameters, and you need to collect the measurement data and to identify those parameters, to validate each parameter. You may take a like optimization approach by allowing the parameter in the load model to vary a little bit and to see which one can fit the measurement data the best. So that will be the final load model. Any question? Okay, so for this memory-based approach, it will be a top-down. You can directly take that model and just use that model. You don't have to go up level by level as the component-based approach. Okay, so this one just gave you more realization about the process of a component-based approach. We start from the characteristic of the load, which are basically the like some indices or the functions for any load characteristic. Okay, so if this region is very simple, or you don't need that level of accuracy. You can basically just utilize those functions to give you the model. Okay, but if it's a larger area, you do need to consider the aggregation of a different type of components. So also you need to follow that bottom-up approach. Go to the next level, which is a load component. So in the load component, you need to use those characteristics to form different type of devices such as heaters, air conditioners, or lights, and then you just aggregate those devices into a different type of load. Okay, so that's load component. Definitely you can directly jump over from the load characteristic to the component. And when you come to the composition, you have to define, give a certain percentage of components to give you that type of load. So the last level will be the classes of the load, which could be a residential, commercial, industrial. You can just go further up by one level. You can directly jump from the load characteristic to the load class and the mix. That's the process. Okay, next, let's talk about the static load model. So the most commonly used load models are polynomial load models, or another name is a ZIP load or ZIP model. So here we assume P0, Q0, and V0 are just rated power and voltage at the initial operating condition. So by initial operating condition, usually we mean steady state condition. Just it can be considered a typical condition. Something like a base value if you want to calculate the per unit value. Then we can define the per unit voltage to be the actual voltage divided by V0, which is the base. So ZIP load is just defined by these two functions. So active power and the reactive power are both polynomial functions, second order polynomial functions of voltage. So P0, Q0 are just their nominal value multiplied by factor. That factor has three elements. First element is a quadratic function of voltage. Second, the linear. The third one is just constant value. So you can immediately recognize if voltage here is a per unit value. So the P3 will pretty much like a constant power component, right? Because if P3 increase, which will directly change P0, will make the P be bigger if P0 constant, okay? And P2 somehow like a current. P2 will have physical meaning similar to current because P2 is multiplying voltage to give you the power. And the P1 is multiplying the voltage square. The P1 which similar to like admittance. Or maybe there is 1 over P1 will be like impedance. So now you understand why we call it ZIP model, because P1, P2, P3 define the constant impedance, constant current, and the constant power component for the entire load. Similarly, for the reactive power, we have Q1, Q2, Q3. They define the constant impedance, constant current, and constant power elements. Okay, that's why we call it ZIP model, because we treat this type of load is formed by three type of elements, which respectively have constant impedance, current, and power in both active power and reactive power. Because we let P0 and Q0 be the rated value of a P and Q, so which means P1 plus P2 plus P3 has to be 1. They together take a 100%. Similarly, Q1, Q2, Q3 together take a 100%. Any question? Okay. The second type of load model, which is also static, is called exponential load model. So you can easily tell this is basically describe a P and Q as exponential functions of a voltage, right? It's as simple as those two equations. So we introduced exponent A for P and B for Q. Okay. So this is much similar. So for this exponential load model, we only just need one parameter for each P and Q, right? But for the ZIP load model, we need 3 parameter. Actually, we need 2 parameter because P1 plus P2 plus P3 equals 1. So you at least need to define P1, P2. Okay, P3 will be the remaining, the rest of 100%. Usually A take a value from 0.5 to 1.8, and B take a value from 1.5 to 6.0. Okay, so this is interesting because when B take the value of 6.0, there's no way you can use a polynomial model to model Q accurately, right? So which means, so both type of model have their advantage and disadvantage. So if you clearly know this area, the load will have mainly 3 type of component, then like constant impedance, constant current, and constant power. Definitely the polynomial load model will be the best, will be better. But if you're not sure those 3 type of component will fully cover everything in this area, maybe exponential load model will not be a bad idea. So if you compare exponential load model to the ZIP load model, so which means, so if you let A be 2, which means the exponential load model will become a constant impedance load. If A equals 1, the exponential load model will become constant current. 0 means constant power. Okay, let me ask a question. So if my load has only constant impedance and constant current without constant power, if I model it by polynomial load model, but now I want to utilize its exponential load model to represent it, what will be A? If the load model has constant impedance and constant current and without constant power, so what is A? Right, will be, it's a reasonable guess will be between like 1 and 2, something, right? Yeah. To estimate A and B, we can do the partial derivative near the voltage with base voltage. So partial P, partial V will be A, and partial Q, partial V will be B. Okay. And because of that concern, we know the exponential load models and polynomial load model, they both have some advantages or disadvantages. So a better idea, maybe we can consider this comprehensive static mode, such as a load model, such as we have maybe 1 ZIP component plus 2 exponential component. Okay, so which means you do need to introduce more parameters. For the ZIP component, you introduce 2 parameters for the minimum. And for the 2 exponential component, you also need to introduce another 2 parameter. Okay, 1 for each exponent. So finally, you have at least 4 parameter to categorize this load model. As that can give you a better representation. Yeah.
So for exponential load model, we are trying to find out A and B, or trying to find out P0 and Q0.
P0, Q0, already know. Those are the base value.
So we are trying to find out the
Yeah.
for A and
Yeah. Right. So if you make A and B be both 0, right? So which is, if you make a B and A be both 0, which is equivalent to get rid of those exponential function. Okay. P will be constantly P0 and Q will be constantly Q0. So that's a load model usually we adopt in the power flow analysis, right? So for each load bus, load bus, we treat it as constant PQ load, constant P and constant Q bus. That's why we call it PQ bus, which is equivalent to constant P, constant power load. By introducing this exponential function, we allow the load can change around that base value if voltage change. So the polynomial function, exponential function, just tell you how the power may vary near that nominal voltage a little bit. Next, we want to talk about the frequency dependency. So if a load depends on frequency, so we need to introduce the frequency deviation, which is in per unit, just the f is if f is the real time frequency, f0 is a singular frequency, so delta f bar will be the per unit frequency deviation. Okay, so we need to bring this one to our load model. So how are we going to model the frequency dependency? We just multiply the ZIP or exponential load by a factor which depend on frequency. So the simplest idea, we just assume the load will change linearly with frequency deviation by introducing two coefficients, two Ks. Okay. KPI for the linear coefficient with IT power, and KQF is with reactive power. We also can multiply the same factor to the P or Q for the exponential load model. The typical values for those key factors 0 to 3 for KPF, and -2 to 0 for KQF. So this one can give you some ideas on for the typical load when the frequency increase, okay, which means the IT power will somehow increase. Most of the load will increase, IT power will increase with the increase of frequency, but reactive power will decrease with increase of frequency. This is what we learn from those typical values. Another thing I have to emphasize in this section. So here we use F, but I didn't use like omega R. Omega R is usually we consider as like state variable for generator, but this is F. F is actually the bus frequency, because we are talking about the load in the system. The load may be far away from any generator. So if this load depends on frequency, so what frequency are we talking about? It's not about a specific like rotor speed of any generator, because it can be far. The frequency means bus frequency. Bus frequency means, so at this bus, there's a voltage phasor. The voltage phasor will have angle, the phase angle. So if you calculate derivative of that angle, you will have a frequency. So that's what the bus frequency means. Because bus frequency is not state variable. Because if we don't treat the bus voltage as state variable, the bus frequency will not be state variable. Bus voltage can change instantaneously. Remember what the difference between the state variable and the non-state variable. State variable cannot change instantaneously because there's a control system or time constant associated with this variable that stops this variable from changing instantaneously. So there's some time constant such as tau factor. The tau means they take a tau time to decay to 37%, right? So if the tau is non-zero, it will take some time to change. But when it's not state variable, there's not such a time constant. Or in other words, maybe the time constant is too small. We don't have to consider it. It may be microsecond, much less in the time frame we consider for stability study. Then it's not a state variable. So which means bus frequency can change instantaneously. So if a load depends on bus frequency, when the bus frequency change, the load also change. And that frequency is what this load can see, okay, at that location. So based on the voltage and current waveform. So even there's some disturbance which can change the waveform, voltage and current, and the bus frequency also change. Okay, that also influence this load. A related quite problem regarding this bus frequency is usually when you purchase a phasor measurement unit like synchro phasor or PMU, okay, usually you cannot place a PMU directly to the generator, right? It will be connected to some substation. So what it measures is actually bus frequency, not the rotor speed. It's not state variable. So which means if you draw the waveform of that bus frequency, you can see frequency suddenly change. There's some spikes on the frequency. That is because of the sudden change of the current and voltage on that bus. When you calculate the derivative of that waveform, they will create some like singular value or very abnormal value, like spike. But that doesn't mean the generator has that jump of a frequency. Because I see some research papers, they try to simplify the dynamic model of power system, and they include the bus frequency as state variable in their equations. Usually I will, when I see such equation, I'll raise the questions, what if I have disturbance next to your bus and the waveform will suddenly change? Will that impact your control algorithm? Frequency deviation is typically calculated using the voltage phase angle, but if you have been involved in any project for data analysis based on the PMU measurements, you actually you will know there's some algorithm you can either use the voltage phasor or current phasor to calculate the angle. They will have certain angle shift, but either way is fine. That will give you the bus frequency. So it can be from either voltage or current.
The function of the voltage phase angle, because under the steady state, we usually use part load to calculate where we can get a single number of angle, but how do we get that function?
So if you measure three phases, right, you have a data in the A, B, C frame, and you do the path transformation, that gives you D and Q. From D and Q, it tells you the angle. Right, you can use path transformation. That's similar to how we estimate the delta for generator. So there are two tables which show some typical value of a power factor, like A, B, and KPF and KQF. So if it may be too small, but if we pick like this is like an oven. If an oven, so the power factor is 1, and A is 2. A equals 2, which means it's a constant impedance load, and B is 0, right? It doesn't have reactive power and doesn't depend on frequency. So this is simply its load. Let's see something else. Like dishwasher. Dishwasher will have some motor in it, right? Dishwasher will have power factor 0.99, and IT power 1.8 is also very close to an impedance load, but they will have a reactive power. And the IT power doesn't depend on frequency, but the reactive power will decrease with increase of frequency. So those values are basically same as what we said in the previous slide about the range. So usually the KPI value are typically positive, and but the KQF value typically negative. The second table shows those parameters in different seasons for different classes of load. For example, for the residential load. For residential load, if it's in the summer, you see, so have both active and reactive power. So for the A factor, that's 1.2. So that's more like a constant current load. Reactive power is like a 2.9, which is like more like a constant impedance. It is frequency dependent. For the winter, A will increase to 1.5. So it's more like something between the constant impedance and constant current. Okay, what else? Yeah, so anyway, those tables just give you some basic ideas. Such tables are useful if you want to consider different type of loads or different classes of load in your stability study. You can, for example, you have a power system model, and you can consider maybe bus 1, 2, 3. Buses 1, 2, 3 will be the residential area, and bus 4, 5 will be a commercial area. So you can take some perimeter here to come up with your load model to give you better representation. Next, we talk about the lighting loads. So in the past, lighting load can be very simple. It's pretty much just incandescent light. Right? This is a conventional. This light has been used for more than 100 years. Later, we have some new type of lights, like a energy-saving light, such as CFL or LED. They actually take a majority of the light, especially in the commercial area. Maybe in some residential loads, they still use incandescent light. So I found this table from a reference, which just give you some comparison of different type of loads. But for this table, we can focus on those 3 type of lights, right, to see the difference. So this column, it will give you the 3 components of the IT power, and that 3 component will be for the reactive power. So if we see the incandescent light, the old one. So its first one is the P0. It's like 87. And Q0 is 0.85. So which means for the old type of light, and the IT power is a majority. So it doesn't have use much reactive power, very little reactive power. And for the IT power, so the constant impedance component will have almost 0.5. Constant current will have 0.6. Okay, so it's pretty much something between the constant impedance and constant current. And constant power part can be ignored. So if we move to the CFL, so which is a blue line. So in the blue line, the IT power for this one is 25, and reactive power is 37. Okay, so power factor is largely changed. And for the IT power, the constant impedance is 0.8, around 0.8, and constant current is -1. Okay, and constant power is 1.2. Okay, so it's already very different from the incandescent light. So when you have more and more the energy saving lights, and the lighting load will behave very differently from the original, like what we usually know as a resistive load. So they are less likely to be the resistive load. Okay, and then we move to LED. For LED, you see also the power factor is very different. So you have both. You have bigger Q value than P value, and for the constant power, constant impedance, you have a 0.58. Constant current is 1, and constant power become negative 0.7. Okay. You may feel those numbers look very strange, but the reason to have those like a negative number, what does a negative constant power really mean? So actually, you can think about this observation in such a way. So we use those polynomial functions, especially second-order polynomial function, to fit how the P and Q change with voltage for those very complex devices, right? And we only use that function to fit a small part of the curve near the nominal condition. That's why those numbers can be very strange. Okay, it may not have better like interpretation on why what does like negative constant power mean. Only when taking those values then to categorize this polynomial function. That function may look very strange, but for the part around the nominal voltage, that's the best fit. Okay, that's basically taught by like a curve fitting method. I use this example to explain why those energy saving light can have very large reactive power. Because what does reactive power really mean? Reactive power means if you draw the voltage waveform, which is at this bus or substation, that voltage waveform can be controlled by controller. If it's next to a generator, the generator will generate a sinusoidal, perfectly sinusoidal waveform. Okay, if this generator is designed well. Then when you connect a load to this bus, the voltage cannot be changed significantly, but current can change. Current is generated by this specific device. So if the current has a very similar waveform, also sinusoid, and in the exactly same phase, that's power factor 1. If that current waveform is lagging the voltage by any angle, like bigger angle, that's not power factor 1. Also, even they have a same phase, which means they reach the peak value at the same time, but the waveform look very different. That's also reactive power. So to summarize, if the current waveform, if we ignore, we just draw the per unit value, like for current and voltage waveform, they look almost exactly the same. That's power factor 1. If they look different, that's not power factor 1. Okay, but different, which means they can have very different phase or have very different shape. So those energy saving light will change, make the waveform of the current be very different from the sinusoid. For this case, if this is a peak value of voltage, that's peak value of the current. So you have to do a Fourier transform to change this blue curve to a harmonic, different harmonic, like from the fundamental one to high order harmonic. First of all, the fundamental may have a phase shift, and they also have some other harmonic. So they will introduce reactive power. Okay, reactive power is just a measurement about how different the voltage and current waveforms are. Any question? All right. Okay, so we learn how to model the static load by considering the load changing with voltage and the frequency, and then and also we know a range of a parameter. Okay, let's see if we don't have enough information. I just want to do a simple stability study. I got a test system and I want to give the load of each bus exactly the same. But what is the best practice I can do without more information? Okay, so if you use any software like a PSSE or TSAT, a PSSE by Siemens PTI or TSAT by Partai Lab, so usually there will be some dialog you can choose some setting. For instance, here it tells you can give some percentage for the constant impedance, constant current, and constant power component. So if you don't have enough information, usually those manuals will give you a default value, will make A be 1, right? Which means you consider IT power as constant current load. B equals 2, reactive power as constant impedance load. So that's the priority which is safe, okay? Yeah. And also, if the voltage below some threshold, if there's some controller, that will change the load characteristic. Okay, so when the voltage is near V0, it can behave like a constant current or constant impedance. But when the voltage is too low, there could be some controller, such as if this load is induction motor. So there'll be some protection control with the induction motor. So usually such software will suggest if voltage below a certain threshold, like a 60 or 70% of nominal voltage, you need to convert the entire bus into a constant impedance load. That due to a couple of reasons. First, it may be similar to what this load really behaves. Second, it can avoid some computational problem, because if you keep a constant current or constant power, the load, the software, the simulation may become a divergent more easily. So those are the best practice. So if you don't know information, or maybe your first simulation, you can just use those settings. You don't have to manually change those values. I believe for most of cases, if you create this case to simulate, those are default value. The software already set it up for you. Okay, next we talk about one type of dynamic load, which is the thermostat controlled loads. A thermal load is a static load and a resistive load. The thermal load, which means you just use this the high resistance to create some heat, right? To change the electric energy to heat, to warm up the house or maybe the living area. But when you add a controller, okay, controller, you want to control the temperature. I want to maintain the temperature at 70 degree F. Then you need to add a controller. Then the load can behave differently. So for instance, the top figure indicate there's a thermostatic control load. I set up the temperature, which could be air conditioner. I set up the room temperature at 70 degree. Okay. So if right now I start from the temperature 72, which is higher than 70 degree, this controller need to turn off their AC. Okay, which means the temperature will decrease. Assume it is a winter. It's right now, like it's winter. So temperature will decrease linearly until a certain point to make this gap be large enough. The controller will turn on the AC. And the temperature will go up linearly. And reach the 72, it will turn off. So it will just switch between off on, off on. Okay. Then the question is, what does this load, how should I categorize this load into either like static load or dynamic load? So if my simulation only focus on one very brief time period, let's see, 5 seconds, 10 seconds, that can be inside of this off stage. So then this air conditioner is not connected to the power system, it's off. Okay. If I only focus on maybe another period, which is when the heater is on, and this also like this load will behave like constant impedance load. But if my studies is covering much wider time frame, right? Then the load will behave as constant power load because it tries to maintain the temperature at constant temperature. Why is a constant power? Let's say right now the voltage is decreased to 90% compared to the first case. But my controller want to maintain 70 degree. So what can I do is I can increase the percentage for on state, okay, but to 55.6%, slightly over 50%, which means when the voltage is lower, your AC will be turned on longer than it is turned off in order to maintain the same temperature. Because it consume the electric energy to heat this entire house. The house doesn't change. The outside temperature doesn't change. The only thing change, which it is the voltage, which means this AC load is constant power load. It doesn't change with the voltage. For both 100% voltage or 90% voltage, it can control the temperature at 70 degree constantly. Yeah, so that's why for longer time frame, it will be considered constant power load. So the question is how to model such load really depend on the time frame of your stability study. If you study like transient stability, which only happen in 5 seconds, 10 seconds, that's not long enough to have the AC switch from one state to another state. you can treat it as like constant impedance load. But if you do a long-term stability study, like voltage stability study, like voltage scenario, usually can take maybe tens of minutes from beginning until finally the system collapse. Then you may need to consider this load as constant power load. Any question? All right, so next one, motor load as a typical dynamic load. Motor load consumes 60 to 70% of total energy of a power system. In today's power system, they can drop 70% of system load during a fault or during the voltage excursions following a fault. When the voltage drop, and those air conditioner or the motor, if it's not air conditioner, it can be some industrial motor. They will have internal protection, so they can also drop. So their impact to the system will depend on where they are. So if they're at the receiving end, they can benefit the stability. But if it's at the sending end, they can make the stability worse because they will change the net load, the net generation in the area where they are located. Air conditioner, compressor, induction motors, they count up to 50% of system load in summer, especially in the hot area. So they can stall if the voltage is low, like a 50 to 65% of the nominal voltage for 3 cycles right after a fault. Once the motor is stalled, it will behave like a constant impedance load, but with low power factor. Okay, constant impedance load can be better to transient the stability, but with very low power factor is not a good feature to the system, which means it needs a lot of current. It will draw 2 to 3 times of a rated current. So at the nominal voltage, you can treat a constant. Those motors, like air conditioner, they can have like temperature control. They behave like constant power load. But if the voltage is really low, they can become a constant impedance load, but with very low power factor. It will need a lot of reactive power. They can largely influence the voltage in that area. The thermal overload protection disconnect the motor if it remains stalled for considerable amount of time, such as like 15 seconds if it stalled at 50% of voltage. It recovers if voltage goes back to 70% of nominal voltage, and that delay the voltage recovery. So what happens is, if you think about it, you have a usually you have a voltage around 20%, but some fault or maybe a number of faults happen that make the voltage in one area to close to be very low. That will make the induction motor near the fault to be stalled. Once it's stalled, it will behave like a constant impedance load, but with very low power factor and need a lot of reactive power. Then it makes the voltage in that area even worse. Then after the fault is clear, when the voltage recover back, and the induction motor will think, okay, so I need to go back. So they will restart. But restarting induction motor also need a lot of reactive power. Okay, the worst case will be some induction motor will keep restart. So that for a long time, that will consume a lot of reactive power after the fault. So that time can last maybe 30 seconds. There's one examples in Southern California, because they have in summer they have a lot of air conditioner load, because the stalling issues, and the voltage take a very long time to recover back. Okay, there are always some percentage of motors are stalled, and then restart, then this becomes stalled again. So in the area with a very high percentage of air conditioner loads, so delay voltage recovery, that is so-called failure or fault-induced voltage, delayed voltage recovery issue will become very serious. Short-term voltage stability and fast voltage collapse are main stability concerns. We'll talk more about such issues in the voltage section. Let's quickly talk about the modeling of induction motor. It is not required for this section, but we can utilize what we know about the synchronous generators, to understand the model of induction motors. So this is the equivalent circuit of induction motors, right? So because induction motor behave as a load, not generator. So for generator, we'll usually treat whatever inside as EMF, electromotive force. But as load, we'll treat this induction motor as some resistor. But this resistor is not constant. They depend on the speed. More accurately speaking, depend on sleep. S here is the sleep of the motor. Okay. S is defined as like percentage lower than the cylinder speed, which means if this motor is operating at exactly cylinder speed, S will be 0, which is like this component is open circuit. They have infinite resistance. If this motor is operating at 0 speed, S will be 1. Okay, so based on this equivalent circuit, you can easily draw the current going to the motor will be the voltage divided by the Z1 is actually internal constant impedance, which is similar to the cylinder readiness we have for the generators, and also that speed dependent part. So the mechanical torque is equal to the power divided by the speed. If you can easily prove this formula, okay. This tell the torque will depend on the S. S will be the percentage deviation from the cylinder speed. Okay, if you draw the curve, how the current will change with the speed. This figure tells. So this value is synchronous speed. For the induction motor, it cannot operate at synchronous speed. It have to be lower than the synchronous speed in order to induce some current voltage inside of the rotor, right? Because the rotor doesn't have like field winding to give you that current. The current is induced by the difference of the speed. So which means if the synchronous speed corresponds to this 1800 revolution per minute, and the rotor speed is very close to this value, maybe 1700. So this green region will be the nominal region for this motor to operate. If it can stay within this region, the motor will be stable. Left-hand side value will correspond to the motor stalled. So when the motor is stalled, based on that equation, the current will be much higher than the nominal current. Okay, the typical current can be, for this case, lower than 10 ampere. But when the motor is stalled, the current can be 40 ampere. Another figure is the torque slip curve. Slip curve on the right-hand side is still correspond to the 0 speed. Oh, this is correspond to 0 speed because slip is 1. When slip is 0, which means it is the signal speed. And also the green region indicates the nominal region for the motor to operate. When the speed decrease, so this direction will be the speed decrease. When the speed decrease, the torque first reach the maximal value, then it will decline. And when the motor is stalled, the torque it will have some value, like close to the nominal operating torque, but speed will be 0. Because the mechanical power is equal to the product of the torque and the speed. So even the torque is non-zero, but speed is 0. It doesn't consume any much energy based on the formula. So if we those don't just give you the some characteristic based on the circuit, but if we want to model dynamic, because it is a dynamic load, those equations don't give you dynamic. We need to introduce differential equation. The first equation is just definition of the slip, okay, which is just a per unit, basically just a negative per unit speed deviation. So for the generator, usually we consider speed to be higher than synchronous frequency, right? So we usually define speed deviation to be omega r minus omega 0. But for the induction motor, usually omega r is less than omega 0. So S is like just a negative speed deviation if we use the convention for generator. And second equation is basically just swing equation. Because if you replace S by negative delta omega r, it basically become a swing equation. And what is the next two equation? So we use V because usually we call the voltage on the low side to be based on capital V, and for the generator side we use capital E. So that's why here we use the lowercase v. So the first state variable is called Vd prime. The second state variable is called Vq prime, which is like two fictitious voltage in the D axis and Q axis of this motor. If you still recognize the two axis model of the generator, those two equations are very similar to the corresponding two equations from the two axis model. Let me bring that model here. So this is swing equation, right? That's basically correspond to that equation. And this is ED single prime as state variable. I already moved the time constant to the right. I just try to make those two have almost like same form. If we consider the round rotor generator, ignore saliency, and so here used to be SQ or SD, so that become SS, right? SD prime and SQ single prime just become S prime. So you see this one and that one basically very similar. Okay, and this one is very similar to that one. But definitely for the similar generator, you have field voltage, but for motor, you don't have field voltage. You field voltage is really caused by the slip because of difference of speed that will induce the voltage. Okay, so this one tell where this field voltage come from. The next equation, this equation is basically talk about how to determine the voltage, real part, imaginary part of that voltage phasor, right? So that is basically almost same as this one to determine the ED and EQ. This equation PE is basically same as the TE. So lastly, the cylinder generator, the mechanical power is controlled by turbine. So this mechanical power or mechanical torque controlled by turbine or governor. Usually can be considered constant in transient stability study. But in motor, that torque will change with the slip following this function. It's not constant. So usually it can be simplified by some polynomial function. Definitely you can use other nonlinear function to simplify the power, but basically that just represent what happened near the operating point. All right, so I just use this example to tell you basically you can borrow the same approach for modeling cylinder generator to model induction motor. And another thing is here some negative sign is really because of for the motor we define the current to be going to the inside of the motor, but generator is currently coming out from inside. So there will be some negative sign difference if you compare this motor model and the generator model. I only have 2 slides left. Do you want to finish? Yeah, we'll finish this session. Impacts on the angular and voltage stabilities. This is one study done by April. That's back to almost like 19 years ago. Okay, just compare different percentage of induction motors and how that can change the system damping. So the red curve will has 45% of the load to be induction motor, and the blue curve only have 30%. So when you increase induction motor, that makes the system tend to swing more. Second example, we just compare the system to simulate the voltage waveform right after a short circuit fault. And if there's no motor load, then the voltage can recover very quickly. Okay, but if you add induction motors and considering the motor can be stalled and restart, if you do a more accurate modeling for induction motor, you can see the voltage can take a very long time to recover. So the load modeling is important to the voltage stability and angular stability. This slide, I want to talk about some basic idea about the memory-based approach to the load modeling. So this it will take a number of steps. First, you need to collect a few memory data on the load characteristic. You need to select some substation which can maybe in each region you pick a representative substation, and also select the representative time, the seasons or days to collect the data. Then you need to identify the parameters by solving optimization problem. So if you already selected the model structure and with number of parameter, by changing the parameter, and you can use the model to do the simulation and to compare to the measurement data. Okay, the best fit will give you tell you the best model. Then you can apply this model for this entire region. If you only just choose maybe a few substations in each area, you can just extrapolate the parameter for this entire region or entire system. This is a snapshot from the memory-based load modeling software developed by April. This table just show you actually, they have user interface. You can choose different by adjusting different parameters and to compare the simulation from this model against the measurement data. So this one just tell by default you can choose a ZIP load model. Right? This is like polynomial component, and you can also definitely add a exponential component. So this part is just an induction motor load. This figure is one example comparing the field measurements with the simulation result using the best model. You can tell basically just match the measurement well, but definitely there's some detailed difference. But if that's not important to the stability study, you can use this model, or you need a better like fine tuning on the parameters. Okay, so this is my last slide. So we take this single lecture to finish this section. Next class we'll move to a frequency regulation session.